Okay, welcome back, and thank you again for being back here. Hopefully you had a nice lunch break. It looks like we'll probably still have a few more people coming in here shortly, but we did want to get started again. So I'd like to introduce our next speaker. It is Dr. Volkens, who is an associate professor in the Department of Mechanical Engineering at CSU. He also directs the Center for Energy Development and Health within the Energy Institute, and his research focuses in part on air pollution-related disease, and he's going to speak today about an emerging area involving citizen science and personal monitors, in which he is a pioneer. So, over to you, John.
Thank you. Can everyone hear me okay? Okay, so I'm an environmental engineer who's masquerading in the Department of Mechanical Engineering at CSU. And I'm actually trained in public health, and so I like to refer to myself as a public health engineer. And it's a great discipline to be in, and there are far too few of us in the world, and I wish there were more, because I think engineers have a huge contribution to make to public health. When you think about great public health discoveries or innovations over the last 100 years, when I ask this question, most people say, oh, you know, vaccines, that's one of these great public health inventions. But what about the seatbelt? What about the refrigerator? Or chlorinated drinking water? Those are all public health innovations that have saved hundreds of millions, if not billions, of lives. And so engineers have a contribution to make to public health. And I'll talk about my very narrow contribution here today. As someone who is trained in the School of Public Health, it's been my mission to insert myself into epidemiology. And Jennifer has borne the brunt of most of that focus, unfortunately, so you can ask her how that's working out. But you know, I've been thinking about air quality monitoring for a while, and one of the things that my lab has tried to do over the last decade or so is develop monitoring technologies for quantifying pollutants that are affordable, accessible, and reliable. And the thing is, we have technology that is reliable and accessible today. It works great, but it's not affordable. And it's difficult to use. For most of it, you need an advanced degree to run these sorts of technologies. And so, as an example, what would it cost you as a citizen to monitor air pollution in your neighborhood or your backyard for a season? You know, looking at PM 2.5, this is the monitor here. This is just one flavor of monitor that might be used to assess compliance with the NAAQS. It starts at about $25,000. And that's just for the box you see there. You're going to also have to pay for real estate. You have to put it somewhere. It needs power, so your electric bill is going to go up. It needs a weatherproof enclosure. And, of course, then it needs personnel. And so all of these costs are incurred on top of just the purchase price of the instrument. You're talking a minimum of a doubling of that cost probably to operate that monitor for an extended period of time. That basically makes this technology the province only of government and academics who are funded by the government. Right? Because no one's going to pay $50,000 to $100,000 to monitor PM 2.5 in their backyard. If you want to know the source of those particles, then you have to do something called source apportionment, which many of my colleagues do, and you're basically talking $10,000 to $20,000 on top of that to do chemical analysis and apportionment of that data. Now, that's for ambient monitoring. For personal monitoring, if you wanted to know exactly what was in the air you were breathing at any one moment, we have technology like this from the 1970s. Basically, what you're looking at is a fish tank pump on your hip, and then you've got this little inlet here with a filter. So if I asked you to go home and ask your spouse or your best friend to wear a fish tank pump on the side of your body and drape a piece of tubing across your torso and walk around with that for a week or so, you already know the answer you're going to get. I think I know the answer I would get if I asked you to do that today. Right? And this is the state of the art for personal monitoring. It's expensive, it's loud, it's bulky, it's problematic. Where does this come from? This technology actually has a legacy in the field of industrial hygiene, where we would monitor worker exposure for about 8 hours in a coal mine or a factory where nobody cared what you looked like, and it was so loud you couldn't hear that fish tank pump, you know, humming away in the background. So we thought, well, let's try and do our best to improve the standard for estimating exposure to PM 2.5 mass. And we did it in kind of two ways. The first thing we did is that we found some components that were part of the computer revolution. And the first one was this little pump. And so many of you have probably noticed that over the last decade or so, if you're old enough to have owned a laptop for that long, that your laptops and your desktops have gotten a lot quieter. And that's because they no longer use fans. They typically use these little piezoelectric micropumps that are about the size of a dime. They're very power efficient. And although this little guy vibrates at a very small amount, it vibrates at 25,000 hertz. What that means is that it vibrates so quickly it can push a lot of air, and you can't hear it. And so this technology that came out of the computer electronic cooling industry, we decided to co-opt and see if we could put it into a little personal sampling pump. And this is, of course, when you have this idea, the first thing you do is you put it together on a breadboard, and you use a lot of glue and tape to make the idea work. The other thing that we benefited from is the 3D printing industry. And so by using kind of rapid prototype electronics and rapid prototype parts, we were very quickly able to make enough mistakes to where we could get a working air sampler with that little device. And we proved that we could get it to work. We then iterated that with a machine design. And finally, we came to this injection molded design that you see here. And so this is essentially replacing that technology I showed on the last slide. But we've gotten rid of the tubing. We've gotten rid of the noise. And we've made it about a third the cost of what the traditional technology is. This costs about $200 for my lab to make versus about, maybe $1,000 to $1,500 is the state of the art. The other thing we did is that we took most of the technology that's in your cell phone, which costs now pennies on the dollar because there are 3 billion cell phones on the planet now, and we put it inside the device. And so it's got things like a GPS tracker, temperature, pressure, relative humidity, Bluetooth chip. And so all of the programming that's done with this device is done through your iPhone or your Android phone. And we actually worked with Apple at that time to develop an interface that looks almost exactly like the programming interface you have on your iPhone, which is really useful because you are already conditioned to interface with this sort of technology. And you can see these are some of the nerdy things that we care about, like what's the flow rate? We want it duty cycling. Are we logging or not? What time does it start? Doing some things like adjusting for relative humidity in the air. With this technology now, we are able to do more scalable measurements. We have over 1,000 of these devices now in operation across the planet in over 30 countries. And the technology has since been commercialized because my lab can't make them fast enough. We've also validated the device against federal reference methods. And so on this plot you're seeing here, we call it the UPass, this technology. That's what happens when you give engineers a couple beers in a few weeks to come up with a name. That's the best we can do. And on the x-axis here, you see the reference concentration. And so what you're looking at, these colors are basically different studies. The blue data is studies from my lab in Fort Collins. The black data is a study from India during the monsoon. This is actually part of one of the largest human exposure studies on the planet that we're not part of, but they're using this technology. It's called the Pure Air Study. And then this study here is some outdoor monitoring we did, and then some of you may recognize this site. This is the AQS site in Fort Collins, where we just compared it to, in clean air. And the good news is that our technology for basically collecting PM 2.5 on a filter works, very well, very close to how to reference technology. So this is what I call a near reference method, which is great. So can we improve upon the standard for estimating exposure to PM 2.5 mass? Yes, mostly because the technology we're replacing is older than I am, and it was due for being booted off the field. But you want your data now. We live in the now generation. We all want instant gratification. The technology I showed you collects PM on a filter over 24 hours. Okay? So you get one measurement a day. Now, while that's well matched to the NACS for a 24-hour measurement, most people want data faster. So say hello to low-cost sensors, low-cost PM sensors. I'm sure many of you have heard about these technologies. They come in various different forms made by various different companies, but they all work the same. They use something called light scattering. Basically, you pull your aerosol through this little area. You've got a laser diode that's shooting a laser in this direction. Particles will hit that laser. If they're flowing over this little photodiode, they'll scatter that laser light. You'll detect the scattered light, and that scattered light is proportional to how much PM 2.5 is in the air. So those technologies were actually invented for process control and HVAC. They weren't invented for air quality monitoring, but they've been co-opted into that. And over the last decade, there have been dozens and dozens of new monitoring technologies that feature these low-cost sensors. And these are just a few of them that have shown up on the market over the last few years. About half these companies are probably out of business now, and they've probably been bought by the other half that are doing well. So of course you might be asking, well, this is really cheap. You know, those sensors cost about $20 each. How well do they work? Well, I can tell you one thing. They are proliferating. I'm sure many of you have heard of the purple air monitor. It uses the bottom technology I showed there. This is the current map of how many purple air monitors are operating across the continental U.S. right now. And that purple air monitor, what you get for $250, you get a PVC end cap. That's the white thing. You get 2 of these little plant tower sensors, and you get a Wi-Fi chip and a temperature, pressure, relative humidity sensor. That's everything that's packaged into that little purple air monitor. And we've been asking ourselves, well, this is 10 times cheaper than the best we could do. How well do these work? Because if these work well, I think the problem's solved, and anyone can monitor air pollution in their backyard. So we had an opportunity to ask that question a slightly different way. This is a study called the Fort Collins Commuter study that Jennifer and I did a few years ago. And the point of this study was to find out whether or not commuters had choices in their daily routine to lower their exposure to air pollution on how they got to work. Now, I won't bother with the results of that study. They're more disappointing than you want to know. But as part of this study, we had 50 volunteers from the city of Fort Collins. And they commuted to and from work on 8 different days, and they wore this backpack with all of this sophisticated air quality monitoring equipment. These backpacks actually cost upwards of $50,000 each. We did not tell the volunteers that they were basically carrying a Lexus on their back for these days. But inside the backpack, we had the classic gravimetric PM 2.5 sampler, so that 24-hour filter sampler, and then we had a research-grade light scattering device. But I'm here to tell you that the technology that we paid $5,000 for in this monitor is almost identical to those low-cost sensors that have shown up on the market. So we've got 45 participants, each monitored for 36 hours, 8 days. We can basically say, well, how well does the gravimetric filter sampler compare on a 24-hour basis to this light scattering device? Because if it compares well to the good instrument, then there's a chance it'll compare well to the really cheap instrument. Our participants essentially went about their daily activities. This is just one study day that you see here, a map of Fort Collins, and these little traces are how we followed people around doing their daily routines. So this is basically like a GPS trace. These circles represent how much time they spent at each of these locations. So you can imagine, this is probably the person's home, this is where they work, and this is whatever excursion they did, at some point during the day. And so these are just 4 people on any given day. The bottom line is we've got a pretty representative measurement of what people do over the course of 24 hours with this study. So here's the comparison of PM 2.5 concentrations measured by what we'd call the gold standard filter method on the x-axis compared to that light scattering device. We like to think of ourselves as fancy engineers, so we call it an nephelometer, but it's really just a light scattering device. It's that same technology that you're looking at on the y-axis. This is a log-log scale. Clearly, there's a correlation here, but there is not great agreement going on. How bad is this agreement? Well, the 1-to-1 line here is black. You can see that not a lot of the data points are falling on the 1-to-1 line. One way to look at this data, and so I'll reframe this data for you, is just to divide those 2 numbers into each other. So if they agree perfectly, then you get the number 1 every time, right? Because they'd all fall along the 1-to-1 line. And so this is the same exact data shown on a 1-to-1 plot. And what you can see is that most of the time, that nephelometer is about 50% off of the truth, right? If they were agreeing perfectly, all the data would show up, and you'd have this tight little band on 1-to-1. So the first problem is, okay, we're off by about a factor of 2. The second problem, and for someone like me, the more concerning problem, is that there's a wide amount of variability. It's not always off by a factor of 2. Sometimes it's a factor of 2 greater. Sometimes it's a factor of 10 lower. So what's going on there? Well, because we did this on about 50 people, 8 times each, we could look at Was there agreement maybe explained by a given person? Here are all our participants, at least up through the first 35. And so this is that same data, that one-to-one number. And so if all, for a given person, you can see, and let's just pick this top person here, not only do you see a lot of scatter across all the data, but even on a given person, a given day, these are probably weeks apart measurements, they still don't agree. There's all this variability going on. So what's happening here? Why aren't these instruments agreeing? Here's a really old plot. And I'm showing you a really old plot because as aerosol physicists, we've known that these instruments shouldn't agree for about 5 decades. Now this plot is, 2000, so it's 20 years old. Okay? What you're looking at here is the signal, the response on this y-axis of a light scattering device relative to 2 things: how large the particles are on this axis and what they're made of. These different lines, okay? And so you can see water, silica, iron, carbon particles, dioctyl phthalate, oleic acid, otherwise known as olive oil. And basically, you can see that if I change the composition of the particle, I go from a factor of, say, arbitrarily 300 units down to 30 units. So you change the type of aerosol, and this instrument, this light scattering device, could change its response factor by an order of magnitude. You change the size of the particle, go from a 1 micron particle to a half micron particle. And again, the response of that instrument can change by an order of magnitude. So the problem is that particles, although we call them PM 2.5, their size and chemical composition are always changing, and these instruments can't keep up with that change. And so we know that they're going to be highly variable and largely unreliable. Now, that doesn't mean that they're without use. These light scattering devices can tell you when it's really high or really low. And for some people, that could be a really useful outcome. But as far as absolute accuracy, we expect them to vary quite a bit. So what causes all that variability in the data we had? This is the same data we collected from that Fort Collins Commuter study. Again, we're just stacking up the participants. And then on the x-axis, the bar length is basically what was their average exposure to PM 2.5 over 8 days on average that we measured them for. And then because we track them with GPS, we know how much time they spent at home, at work, in transit, and so we can apportion the variability in their PM 2.5 exposure to these different microenvironments. And you see a couple things. One, people get exposed to widely different levels of PM 2.5 on any given day. 2, this is just looking at this inner box, participant 25. Your exposure changes dramatically from one day to the next. It's not always the same. And where you get your exposure, right? Like why on day 2 did this person get 3 times as much exposure at home as on day 8? And did they not work on day 8, or is their workplace really clean? I don't know. All these were during the week, though, so these aren't weekend measurements. But the bottom line is that because your exposure to microenvironments is changing so much, it's likely that the flavors of particles passing through the instrument are changing as well. Okay, so you want your data now. You can have it, but don't expect a lot of it in terms of accuracy because we know that PM comes in too many flavors and sizes for these low-cost sensors to do a great job. The next thing we thought was, okay, well, that was for indoor PM or personal PM exposure. What about outdoor PM 2.5? It's more, people tell us it's more homogeneous. Every city kind of has the same sources of air pollution, so maybe these low-cost sensors will perform better outdoors. We were fortunate to be funded by NOAA to basically repeat the same sort of experiment in downtown Fort Collins. So what you're looking at here is a little box that we put together. Inside, we had one of those low-cost aerosol sensors, the purple air monitor, because those are very popular. We've got our gravimetric sampler next to it. We've got some huge battery packs so that we could run these things for several days at a time. And so we set these up on light posts working with the city over the course of a few months. And we also set up reference monitors, essentially the federal reference techniques, so that we could get a good measurement of what true outdoor PM 2.5 was at these locations, regardless of what our little filter sampler that we think is good would tell us. We set up this network in downtown Fort Collins. This is a pretty small network. We're looking at kind of a mile by a mile here. And so at most of them, we had 2 purple layers, 2 of our little low-cost samplers, and then a number of sites we had that 16.7 liter per minute federal reference method, and this is the air quality monitoring station for Fort Collins, so we also set up shop there. Okay. Now I'm plotting on this graph a time series of how far off the bias of those purple air monitors was relative to the federal reference monitor that was right next door for a given 2 or 3 day period. And the bottom line is the story is the same, right? So these colors are the individual monitors. The bars are just the average for that monitoring, for that 3 day monitoring period. And you can see you're off by 30%, you're off by 100%, you're below by, 25, 50%. On average, they're off by about 30 to 50% of truth. And these are just, air quality concentrations reported by the Air Quality Monitoring Station in Fort Collins over those times. They're plotted over here. You've seen this data. It's the same sort of plot where it's looking at now bias in percent terms. And so now this is basically our entire network, all those measurements relative to the Air Quality Monitoring Station that was co-located. These gray bars are their EPA performance criteria. So are you within 20% of the reference method? That, if you are, you're almost a reference method yourself. If you're within 30%, or if you're within 50% of the reference method, right? And so you can see, actually, most of these data are not even within 50% of the truth. However, we had that little filter sampler next door, and so we asked the question, what if you could calibrate these monitors in situ? Maybe just once per month. You take a filter sampler and you update the data from that low-cost sensor. And you can see that even with one filter sampler one filter calibration taken per month, we can shift this distribution right on 0 so that we get a nice, more representative measurement, but we can't get rid of the bias. Only when we take a filter measurement every time with the light scattering device can we make that low-cost light scattering device look like a reference instrument. So there's kind of 2 good things here. 1, our filter sampler works pretty well. And 2, if we pair it with the light scattering device, then we can start to get near reference quality data out of these low-cost sensors outdoors, which is exciting. So, do we get better results outdoors? Not really. Okay, so the next thing we thought was, well, we can develop this technology. It's not that expensive to make. One of the things that's really expensive, though, is the cost of deploying them and operating them. But we've got a lot of concerned and engaged community members in Fort Collins who might run these samplers for us. And so we partnered with NASA to do just that. Now, I'm sure most of you know that NASA has these satellites that are circling the planet, and they're measuring something called aerosol optical depth. They're literally just taking a picture of the ground surface and measuring the sunlight reflected off that. And if there's less sunlight on a clear day, that means there must be air pollution in the atmosphere. So that's aerosol optical depth. This picture looks like the satellites are painting the Earth. That's actually not right. But it's a good analogy because they're basically circling the planet measuring air pollution in many places where no air pollution monitors exist. When John mentioned that global burden of disease study earlier today, how do we know that people in remote parts of India are exposed to what levels? It's actually data from these sorts of satellites. The satellites, depending on who you talk to, are not terribly accurate, but like the purple air monitors, they're probably accurate within about 30 to 50%. And so they can tell you where areas there's really high air pollution and areas where there's really low air pollution. But of course, NASA's always interested in proving to Congress that they need more money, so they want to make these satellites more accurate. And so they worked with us to essentially try and do that, to generate a data set by which they can calibrate future satellites. So the idea here is, what if we can make a monitor that measures PM 2.5? Well, we've done that already. We also can make a monitor that measures aerosol optical depth. And then if we can deploy 100 of them, instead of paying graduate students, who are cheap, but not cheap enough for a 100-monitor network, what if we just went to the community and asked community members to deploy the monitors for us? We can make the technology, as I showed you before, with that Apple iPhone interface, fairly easy to use. So that was the birth of this SEAMS project, Citizen-Enabled Aerosol Measurements for Satellites. The idea being here, can we basically create a network of what I'd call near reference quality air monitoring stations? This is just the next generation of the technology I showed you before. We put one of those low-cost sensors in there. We've got our old filter sampler. We've got a little lithium-ion battery, a little Bluetooth chip. This is what the little device looks like that you'd set up in your backyard on a tripod. And with this instrument, you can measure both the satellite product, that aerosol optical depth, and PM 2.5. So we ran a pilot study in Fort Collins. This is just a map of Fort Collins, and these are some of our monitoring stations. This was happened last winter. All of this data was collected by citizen volunteers. And lo and behold, we actually found some really interesting results. So this is just a time series, from December, is that 1st through December 3rd in Fort Collins. So these are 1, 2, 3, 4, about 10 of our monitoring stations. And what you see here, this is that real-time data that's been corrected to our filter measurement, is that at a couple of stations, right around, starting at 6 p.m. until about, 1 or 2 a.m., you get elevations in PM 2.5, only in certain monitors, though. And so we looked at this data a little bit closer, and we found that these elevations are only coming from this part of the city. Now, if you're not with the city of Fort Collins, you can probably guess, because the people who are with the city of Fort Collins know the answer, what's different about the homes in this part of Fort Collins or the city itself? Breweries, good guess. Nope. So the problem with Fort Collins is we have breweries everywhere. So, you can't go anywhere in Fort Collins without being within 100 yards of a brewery. No, this is Old Town. And so this is the part of Fort Collins where the housing stock is predominantly 75 to 100 years old, which is to say most of those homes have working fireplaces. And so what we think we've found is a source, a part of the city where wood burning is happening on cold winter nights. A really interesting outcome of this citizen campaign that we did. So NASA was pleased, and they funded us to move shop to Denver, which we'll do this summer. And we're going to scale this up. So this is a map, kind of our area of interest for Denver. These are the existing air quality monitoring stations that CDPHE is running. And on top of that, we're going to layer in our monitoring network that's going to look like this. And what's cool about this is that these stations will all be connected to the user's home Wi-Fi. So we will stream all this data to a common website that will make available to the general public. And so everyone can see each other's data. And hopefully then we'll learn more about local air pollution sources in Denver as well. And because we're capturing filters, we'll be able to speciate those particles for things like black carbon or metals or ions. And so we can start to learn about the sources of air pollution and whether there are gradients across a region like this. And of course, we'll also try and satisfy NASA's goal of developing a next-generation data set that their satellites can be calibrated on when they launch new satellites in a year or two from now. One of the fun things about this project has been because we have thousands now of these samples being collected, we have a need for real high-throughput analyses. We typically pay graduate students to analyze the filters, but when you're analyzing 3,000 filters a year, it's going to impede someone's ability to graduate if we just pay them to analyze filters. And so we created this little device. I don't know if this will play or not. Yeah, this is Astrid, which stands for Automated Student Replacement Device. And so Astrid is a robot now by which we analyze over 300 filters a day just in this little temperature and humidity controlled box. And the best, and of course most ironic part of this is that the mechanical engineer who designed this was an undergraduate, and so he basically designed his replacement and did a really good job. Okay. I didn't do any of this work, and so I want to acknowledge the great students and collaborators at CSU who really went out and collected and analyzed this data, and of course I want to acknowledge our funding as well. Thank you.
All right, do we have questions for John?
You mentioned speciating the particulate matter. Can you potentially use it to do sort of in vitro tox analysis, throwing it on cells? Because it looks like some of the you could potentially set some of the stations up right near roadsides. I mean, I know these are on people, but you could potentially have stationary ones which would collect collect some of the stuff right by the road and then compare that.
Yeah. So the answer is probably. It depends on the type of in vitro tox you want to do. In a former life, I did quite a bit of in vitro toxicology. And the issue is we only collect about 50 to 100 micrograms on each filter. And so extracting that off and getting into a solution where you can put it onto cells can be challenging because you typically need to have much more of a heroic dose to get a response in solution. But the answer is yes, you could use it. I mean, the nice thing is we analyze our filters using non-destructive methods. So light transmission for black carbon. We weigh it for the... we use XRF for metals, we weigh it for gravimetry, and then we use things like FTIR for organic carbon. And so we have the filter left over after we're finished.
Great, thanks.
Thanks. Wes Wilson with Be the Change. How transferable will this pocket-sized technology from particulate matter over to the methane, benzene, the toxic gases coming from fracking?
Stay tuned. We're working on that right now. Methane is very difficult to measure, and the federal government has put a lot of resources into low-cost sensors for methane over the last decade. Nothing is yet to materialize in the ballpark that we've shown that can be on a wearable monitor, but we are very close to technology that can monitor at least time integrated for things like benzene and alkanes. And so we have a prototype VOC monitor in the lab right now, and with a little bit of funding, we'll be able to push that into the field.
Okay, sign me up.
Jim Crooks from National Jewish Health. Do you ever think about applying this to pollen monitoring?
Yes. I think we can do pollen monitoring actually even cheaper with citizen science. This is only at the idea stage now, but you're not the first person to ask me this, so I've been thinking about it over the last few weeks. I think we could literally have citizen scientists just put microscope slides out in their backyard. And pollen accumulates everywhere, right? And so all we need then is to take that system I showed with the last robot slide and automate the optical analysis through a microscope. And we could basically just mail people glass slides, have them ship them back to us, and rapidly not only count but speciate pollen in neighborhoods. So that's as far as I've taken the idea. But I do think it's possible, yeah.
Hi, I'm Jeremy Newstifter with the Department of Public Health and Environment. It's on. I had a question regarding the exposure study that you did in Fort Collins. How did you get exposure? How did you differentiate exposures during the commute compared to, if you want to go back. I was thinking of the map.
This one?
Yeah, so how did you understand exposures during the commute compared to at home and at work? I understand with a light scattering monitor, you're getting real-time monitoring data, but with the filter-based monitoring approach.
The the gravimetric technique, like I said, costs about $3,000. So I said the backpack costs $50,000, and that's because we have some real-time monitors in here for things like carbon monoxide, black carbon, ultrafine particles that cost $10,000 each. And so by having these recording data every 10 seconds, we also have a GPS in the backpack and an accelerometer. We have an accelerometer on the person and an accelerometer on the backpack, so that if they're moving together, we know that you're wearing your backpack. And so, that's a big problem, right? Because you trust people. And so we were a little bit relaxed. We said between 6 a.m. and 8 p.m. you had to wear this thing to get your reward. I can't remember what we gave them as a reward, Jen. Probably like $20, but they did. They did for the most part. And so we basically have that real-time data stream, and then we have a GPS tracking on them. We also measure temperature and relative humidity on the backpack. It turns out when you leave a microenvironment like your home and go outside, While the GPS might be slow to catch up, the temperature and relative humidity change really quickly, and so we can see that transition happen. And so we kind of merge all those data streams to assign these microenvironments. And we know where you live, so it's pretty easy to just draw a circle around this house and say, you're at home now or you're at work then. And so that's how we deconvolute it into those microenvironments. Yeah.
Good afternoon. Mark McMillan with the State Health Department, Air Pollution and Control Division. Thank you for a good presentation. I was thinking a little bit about this talk in terms of how information about exposure may also change behavior. What I pick up, for example, from that map is we know about exposure based on behavior, but I wonder if there's some opportunities to change behavior based on exposure information. So perhaps that informs our transportation options when we know more real hand in terms of what's happening on the air quality front. I don't know if you have some thoughts or perspectives about that.
Yes, I do. I think that behavior is obviously one of the largest drivers of personal exposure. I mean, the outdoor environment, of course, gets inside the home, but your own personal behaviors and choices do drive a lot of your exposure. When I showed this microenvironment stuff, one thing we found that was surprising is that a lot of exposure actually happens in restaurants because of the cooking that they do. And we've been discussing whether or not aerosols from cooking are as harmful or meat charbroiling are as harmful as aerosol coming out of a diesel bus. But we do see a lot of variability, and it looks to be due to behavior. And of course, the home exposures in red vary quite a lot as well. I think that citizen science presents an opportunity to learn more about behaviors and how behaviors and exposures are tied to each other. I think we're really only just beginning to scratch the surface on that, at least in this country. So I do think there is great potential. And the other nice thing about citizen science is that when you get someone wearing a monitor, they start to think about what they're actually doing, and they are being exposed to air pollution. So that, in some cases, kind of turns a light switch on in their head to say, oh, wait a second, I'm getting exposed to air pollution and you're providing me information on how I got exposed. So I think that there's potentially a pathway to behavior change. So that's my glass is half full answer. The glass is half empty answer is you don't change behaviors. It's really hard to change behaviors because we're human beings and we like to do things the way we like to do them.
Did you have, Tom Butts with the State Board of Health, did you have information on vaping or tobacco use or things like that for these
good question.
participants as well?
So we collected these data in 2015-ish. Yeah, so vaping was kind of just starting to get on the scene then. But we purposely recruited non-smokers into this study for two reasons. One, smokers are dumb, and so we don't want to study them. No. Primarily because we knew that the smokers that cigarette and secondhand smokers would blast the measurements we were going to do. And as part of this study, so from the exposure standpoint, it's not as big of a deal, but we were looking at markers of health. So we looked at markers in blood, we looked at blood pressure, we looked at arterial stiffness, and those things we expect to be dramatically different in smokers. And we didn't have the sample size to include smokers, so we excluded them from the study for largely those reasons. Yeah.
And I don't know the status of indoor vaping use or home vaping use. Did you have any data on that as well?
Not from this study.
Okay.
It's something we're really interested in looking into more because vaping is so different than the fundamental combustion chemistry that happens in a cigarette. And the vaping industry, as I'm sure everyone knows, is so poorly regulated right now. So what's the chemicals that can be in that vaping juice, I think is what it's called, can be anything. And the other thing that I've been thinking about a lot is most of those vaping juices are acidic just for the pH balance of what they want to do. And I think also it's easier to deliver nicotine to the blood when you're at low pH. So if there's metals in the vaping instrument, then you're going to have metals in the aerosol. So these little vaporizers are probably putting metals directly into the bloodstream. So you've got this whole new series of, maybe not pHs anymore to worry about, but things like metals in the blood. Yeah. A lot of questions, not a lot of answers for that one.
Okay. Any final questions? All right. Thank you, Dr. Volkens. Okay, so our next item, our agenda item, is climate in Colorado, and we are going to have two speakers. But first, I'm going to invite Taryn Finnessy down while we pull up her presentation. So Taryn is the Senior Climate Change Specialist for Colorado. So she provides advice on climate change-related matters and policy and works across our state agencies to integrate scientific and policy innovations and increase the state's ability to address climate change impacts and reduce emissions. So please welcome Taryn.
I'll use the podium. Dresses and lapel mics don't work. Can we engineer a solution for that one? Hi, and thanks for having me. I think one of the challenges of sitting here and listening to people talk before me is I come up with a running list of, ooh, I should have included something on that, or ooh, I should have included something on that, and I only have 15 minutes. And so there's a whole lot that I'm missing in this, and I'm going to start by saying that, and I'll try to touch on as much as I can, and then I know Rosemary is going to touch on some of the more air quality pieces that I'm going to just kind of breeze over. And then I know there's a wildfire session after this, so even though I have a couple slides on wildfire, I'm not going to get too much into that except for the climate connection. So now that I've completely discounted my entire talk, I'll get started. So let's start with what we know. In Colorado, we have warmed 2 degrees in the last 30 years, 2.5 in the last 50, and we are projected to warm an additional 2 to 6 degrees Fahrenheit by 2050. So that's just mid-century. And that is across all scenarios, across any data that you look at. Science agrees that we are warming. We know that from our observations, and that we will continue to warm. Precipitation is a little bit different. I'll get into that a little bit more later. We don't know exactly what we are going to see with regard to precipitation, but what we do know is that with warming, it is enough of a signal that we know that things like water availability will be lessened as a result of just the warming. So what does that mean when we start talking about warming and context? We did an analysis a couple years ago looking at just temperature. So if you warm 2 degrees, Denver becomes more similar to Pueblo, and we're talking annual cycles here. And we did this because when you talk especially to policymakers and decision makers, in a place like Colorado where we have 40-degree swings day to day, or it's 70 degrees 2 days ago and it's now snowing and all your tulips are crying, people don't really, it's really hard to conceptualize what 2 to 6 degrees means, right? Because we have daily shifts much greater than that. But we're talking about annual cycles here. And so we wanted to contextualize what does that mean as far as what the climate of our area would look like. So 2 degrees, we look more like Pueblo. 4, we look more like Lamar out on the eastern plains. And 6 degrees, you have to go outside the state boundaries. And we look more like Albuquerque. But this doesn't take in anything besides kind of annual temperature. And recently, about 3 months ago, the University of Maryland did a U.S.-wide analysis looking at a whole host of other drivers that influence kind of annual climate, including precipitation and moisture and humidity and all of these different elements. And it's a more robust analysis than what we had initially done, which was just kind of a back-of-the-envelope analysis. And what they found is, does this work? Yes, it does. Yay. So this is Denver. So looking at Denver, our by 2080, so it's a slightly different time frame, our annual climate would look more similar to what you see in Borger, Texas. And right now, summer temperatures in Borger, Texas are about 9 degrees Fahrenheit higher than what you see in Denver. And I threw up mainly because I did this for a talk that I gave this morning, a whole host of other Western communities. The talk was for the National Park Service, so some of them are like random rural communities. But you should get on this and look at it, because it's really interesting to see some of these shifts and changes, and just exactly what it means for what we expect to see with annual temperatures. And what we expect is that, especially with regard to summer temperatures, we'll see warmer temperatures in those summer seasons. And that is problematic for a whole host of reasons, not touching upon the water issue at all. So these are a whole list of components of public health that are impacted or affected or influenced by climate change. But for today, I'm just going to be focusing on the outdoor air quality. But I wanted to put this up here because I think that this is all intertwined. And going back to this slide of looking at 9 degrees increase in summer temperatures, that really it shifts our summer temperatures so that the amount of degrees that we have over 90 degrees every year. Right now, it's depending on where you are in the state, it could be anywhere from 10 to 35 days that are 90 degrees or warmer in the state. But going out to mid to late century, that increases substantially, sometimes by 3 or 4 times. And so obviously from a health impact, even just extreme heat has severe impacts, as does flooding and vector-borne diseases. Drought, which is another area that I work on, we'll get a little bit into as we start to talk about wildfires. But that obviously those extreme events have huge impacts. And then mental health and well-being, which I think is something that we don't talk enough about, has a nexus with all of these, including with the outdoor air quality component. So I just throw that out as food to think about, and all of the things that I didn't have time to include in this presentation. So when we talk about climate change, a lot of times we talk in terms of CO2 or CO2 equivalents, and that's because CO2 is the gas that we have the most of. It's not actually the strongest global warming gas that we have. We have things like methane and HFCs and black carbon. Some of those have been mentioned today, that actually warm the atmosphere more efficiently. They have a higher global warming potential than CO2, but we have the most of CO2. So where are these things coming from? This is kind of our sources. We have mobile sources and stationary sources. We have agriculture, oil, gas, cities. In Colorado, our largest source of greenhouse gas emissions is from power production. Our second largest is from transportation, and our third largest is from kind of our built environment. And nationally, that's slightly different. Transportation has superseded the power sector for the #1 source of greenhouse gas emissions. And the interesting thing about transportation is that it's the only sector that's projected to continue to grow. We're getting more efficient with our buildings. We are changing our sources of power, which I'll get into both of those later. But we are not necessarily changing how we move as rapidly as we should be. So how does climate change influence air quality? This is the part that Rosemary is going to get into a lot more, so I'm just going to kind of breeze over this. But I started my career working at EPA headquarters in D.C., and one of the programs that they ran within our division was an ozone program, and they said ozone is good up high, bad down low, or bad nearby. And so the idea of all of the related, as you warm temperatures, your VOCs and your NOx increase, so you get lower or poorer ozone quality, or you get more ozone and poorer air quality. But we also have the impacts of allergens that are in the air, as well as just changes in weather and pattern. And remember, the weather, especially in Colorado, influences a lot of things like our precipitation patterns, right? And so we're not getting, if we're shifting our precipitation patterns, we're not necessarily getting rains in the same way that we have, which has an influence on allergens and kind of also growth patterns. This obviously has a lot of health impacts and health implications, and I am going to totally breeze over this because it'll be covered by the next presenter. So the increase of our emissions, be it from any source, either through CO2 or any other kind of greenhouse gas emission, obviously perpetuates all climate change impacts. And we are just kind of on an upward trajectory as far as our emissions on a global and national scale. And then we also have increase in ozone and fine particulates as a result of climate change, and then fires. And I want to talk about fires because I think it's one of those things that we all think about, and it's all awful while it's happening, and then the fire goes out, and we don't necessarily think about the subsequent impacts. And then, within Colorado, obviously, especially within the non-attainment zone, ozone is something that we deal with anyway. But as we go forward under climate change conditions, we can perpetuate that. The thing with the climate change is that it's not necessarily introducing new challenges. It's amplifying and intensifying some of the challenges we already have. And that's really kind of across all sectors as far as climate change. So let's talk a little bit about wildfire. Wildfire has increased substantially in the last decades in the West and is projected to continue somewhere between 50 to 200%. And I apologize to the people who are speaking after me. If I get any of these stats wrong, you can actually just like shake your head or raise your hand and be like, no, stop talking. But or just contradict me later on. But it's increasing substantially over the last decades and is projected to continue to increase. Now, part of this is just because of forest management practices. We have about a century of fire suppression practices within the western U.S., so we have an incredible buildup of carbon within our forests, really, really dense forests, that when they do burn, they tend to burn hotter and faster. And so you couple that with climate, which in Colorado we are seeing increased trends in drought, increased trends in higher temperatures, decrease in soil moisture. So really what we're creating with warmer temperatures is much thirstier ecosystems. And when you get these thirstier ecosystems, there's a whole host of things that happen, but you also couple that with the higher temperatures, and you're stressing the ecosystems. And more stressed ecosystems, more stressed forest stands are also more susceptible to things like pests, and so we've seen increases in sudden aspen decline and pine beetle or bark beetles across the West, and all of those also have implications when you start talking about wildfires and seeing things burn. And so we have seen larger wildfires, more intense wildfires, more destructive wildfires, kind of all across the board. Since 2010, we've had the 3 most costly wildfires in Colorado. Our fire season has changed, right? It used to just be a seasonal thing. So we had to deal with it just during the summer months. Now it's year-round. We get fires in January. And like I said, there's many factors that are incorporated into this. But from an air quality standpoint, fires obviously are burning a lot of material that is going into the air and being transported based on the winds. So there are times, obviously, where it's getting transported into highly populated areas. There's respiratory impacts as a result of that. We see increases in black carbon. We see increases in hospitalizations as a result of these fires. And this is all just, air quality. We're not talking about the kind of economic, mental health components that also come with this. But this is something that I think we're going to continue to deal with within Colorado going forward as we can continue to warm, because drought is going to continue to be something that we deal with in a much more prolonged, severe, and intense manner. I wanted to bring in the equity piece of this, because the longer that I do this, the more we start thinking about how to be equitable and how our policies and practices impact the population and the communities of Colorado. And very similar to kind of air quality and exposure, there's an equity issue with it. And so we want to make sure that in finding our solutions, not only to climate change and how we address these, we're being equitable and not putting already at-risk populations in more vulnerable situations, and are coming up with solutions that are within reach of all of these populations as well. So what are we doing about it? And I know I only have a couple minutes left. We are addressing all facets of emissions, but really we're focusing our attention on the top kind of 3 sources of emissions at a really, with a lot of emphasis, and then the other sources we're looking at as well, but again, we don't have time to talk about that today. So we're changing our sources of power. Colorado was one of the first, we were the first state to have a voter-approved renewable energy standard way back in 2004. It has since been increased multiple times, and our largest utility has come to the table and said that they are going to decrease emissions substantially and actually are going to go 100% carbon neutral by 2050. So that's Excel. But in addition to what we're seeing from the utility sector, there's a whole lot going on with the regulation sector. I don't know if any of you guys were involved in the legislative session. If you were, congratulations, you made it through. You're still standing or still sitting. But it was pretty crazy. And there was a lot of action with regard to what's kind of happening on climate change. And a lot of these components have nexus with AQCC. And so this is just a list of climate-related legislation that passed with this, and some of the bills that have a nexus with AQCC is the collection of long-term climate data. So that's Senate Bill 96. Senate Bill 181 has an AQCC connection. And also 1261 has AQCC connection as well. And so lots of components there. It also codifies our greenhouse gas emission reduction goals and takes them out to a longer time frame. So these were initially in an executive order and have now been put into legislation. And so now the real challenge comes in figuring out, well, what does that mean and how do we achieve these goals? How do we implement these? I think that the easier piece is the legislation and the mandates, but actually putting it into practice is where it becomes really, really challenging. But with all challenges, there's also opportunities, and I think we should remember that even though climate change is really big and really daunting and really overwhelming, there are opportunities that exist out there. We have seen a huge spike in clean energy jobs across the state of Colorado in all 64 counties, and we've seen huge increases in installation of renewable energy sources, which are providing huge benefits to rural Colorado as far as revenue streams. During the 2018 drought, we actually heard from producers that the reason they were still in business is because they had renewable energy installments on their land, and they can bring a huge amount of resources in there. Anywhere, we've heard some large-scale producers that have brought in anywhere from $5 to $10 million as a result of the leases that they have, and we've also heard from counties that have been able to continue providing core services because their revenue was increased as a result of renewable energy. And so these are really big opportunities to also examine. Changing how we move, electrification, and corridors and charging. Obviously, with transportation, if we can clean up our energy grid, then we can move towards electrification and cleaning up how we move with transportation. And we're seeing a lot of incentives and efforts on this as well. It's a little bit of a chicken and the egg right now as far as having the corridors, having the vehicles available with range, but this is changing so rapidly. Really, like every couple months, we see changes in kind of what is available for corridors and cars, and I know that the Energy Office has now finished the contracting to electrify and have charging stations roughly every 50 miles on all the major corridors within Colorado, and those will be going in 2020. So that's great. We're going to see an increase in cars available as well, so start car shopping. And to support that, we also have EV legislation that went through during the legislative session, and this is just a quick list of some of that legislation. Again, I'm going over, so I'm going to go quickly. But again, opportunity. Not only is there an opportunity from a savings standpoint for an individual savings, which comes pretty big. The annual fuel savings and maintenance savings cost is absolutely measurable. From an economic standpoint for an individual, it's estimated by 2050 to save Coloradans about $29.1 billion just in maintenance alone. But then from a health standpoint, by 2050, we're looking at $9.7 billion in savings for Colorado just for reduced greenhouse gas emissions, right? So this is addressing some of those air quality components of cleaner air, less ozone, less VOCs, all of those elements. And then changing our built environment. You know, obviously the most cost-effective energy is the energy we never use, and buildings nationwide use about 42.2%, or actually this isn't nationwide, just within the state, use about 42% of our energy. And so really looking at energy efficiency measures, and again, this is where that equity piece comes in, really making sure that we're helping at-risk populations, we're helping low-income populations, we're helping minorities, we're really making sure that this isn't just for the rich who can afford to put solar panels on their house. This is really targeting everyone. So we have programs in agriculture, we have programs in K through 12, we have residential, we have commercial, we have industrial, really trying to take a comprehensive approach at what we're doing. And again, we had efforts this legislative session that looked at energy efficiency legislation. We are coordinating and collaborating. This first one, 1231, was actually a collaborative effort, not only with national organizations, but also with U.S. Climate Alliance states to kind of standardize. So these bills had some similar foundations, so it provides some certainty to industry so that they're not having to figure out which regulations are applicable in each state. There's some kind of core values and core components of all of these regulations across the state. So I know, our regulation is pretty similar to what we see in the state of Washington as well. And then I just wanted to mention that as part of the update to the Colorado Health Assessment, climate change has been identified as one of the key elements of that to look at. And so as that process is going on and being updated, climate change is one of I believe, the top 3 elements that's being integrated into that. And that's been a really fun component to be involved in. So look forward to that when it comes out soon.
Thank you so much, Taryn.
You're welcome.
Great. And if it's okay with everybody, we're going to hold questions, and thanks for holding tight here, and then invite our next speaker down. And John, I think you're going to introduce the next part of the panel.
Okay, great. Continuing on with the theme of climate change, I'm pleased to introduce Rosemary Rochford, professor of immunology and microbiology, and importantly, co-lead on the University of Colorado Consortium on Climate Change and Health, and trying to galvanize and spearhead activities here. Rosemary, good? Yeah.
Thanks very much. And I have 2 hats that I wear. The first hat is a professor of immunology and microbiology, and I study a climate-sensitive disease, malaria, which is not relevant for Colorado. But I do give lectures in this hall to the medical students, so it's nice to see it full of people and see what it's like when it's full. It's nice to see your faces here. The other thing is I'm director of the CU Consortium on Climate and Health, and that's in the context of which I'm talking to you today and sharing with you what I've learned by working with my colleagues there. I'm not a climatologist, but I'm going to bring some of that information to bear. So we talked about evidence, John Samet, at the beginning of this, and we do know that the temperature is increasing worldwide, and the data from scientists is actually pretty clear since 1880, and the measurements from a number of different groups, and this is data provided on a NASA website. So there's consensus that the temperature is increasing, and the important thing when we look at this is that we have an unprecedented global experiment underway. And why do we say that? If you look at this slide here, on the y-axis here, this is CO2 in parts per million. That's 100 up there to 400. And this is over thousands of years before present. That's the scale on that x-axis is really important. So we're talking going back 800,000 years, and you say, how do we know that? That's because scientists can take cores into the Arctic ice and sample those cores and measure that CO2, and that's actually some work being done here in Colorado. So you can see this natural variation in CO2 over the hundreds of thousands of years. It goes up and down in a natural cycle. However, what you can see in 1813 it was at 280 parts per million, and in 2017 it reached 407 parts per million. So it's way off this scale, and this is where we start worrying, we've been worrying about climate change. And the impact, if we look at this, this is a map of the entire planet here, and observe change in surface temperature over this period from 1901 to 2012, it's really striking the increased temperature across the world on average. So what we're now trying to do, and scientists projected as part of the IPCC, is look at the relative concentration pathways, or RCP. And these are climate modelers doing this effort, take supercomputers to put this data together, and project different types of pathways of relative concentration of CO2, and how does that model work. So in one pathway is 2.6. It might be 420 and 2100. Another pathway, 4.5, is 540. RCP 6 would be 625, and the RCP 8 is 930 parts per million. And this slide over here sort of gives a sense of the variation in those models. But what we're going to look at over here is if we just focus in on this, and that's just the same graph I showed you there. If we go to RCP 8, that's a 3.2 degrees to 5.4 degrees centigrade average, and that's not good. So if you look at this, this is if all countries in the Paris Agreement come up with their nationally determined carbon CO2 emissions. It's still going up, but at least it's not there. Business as usual is actually that red line right there. And what we'd really like to do is get down to here. So we've got this temperature increase that we've seen, and I think one of the things when we talk about thinking about how does heat, what does it matter if it goes up a degree or 2 degrees, and how do you present this data? And I really like this slide. This is from Jerry Meal this is from the University, NCAR's National Center for Atmospheric Research, and they have a university sort of educational site. But if you think about, everybody understands sort of the bell curve, right? And we think about mean temperature, which is our previous climate here. And if the mean shifts, which is what we're talking about, the mean of everything, it's going to shift that over there, but it's a bell curve, which means we're going to have less cold weather, we're going to have more hot weather, and record more hot weather. And that's what we're already seeing as we're moving that over. And the key is not to keep it moving over further. But I think that bell curve really helps us understand that, and just always remind ourselves the difference between weather is what we're experiencing today. We can't think about climate change when it's snowing right before Mother's Day, but this is Colorado, so actually that's pretty consistent. But climate is the average of temperature, so it's an average, it's a mean over a period of time. So two very different things. So always remind people about the difference between climate and weather. Weather's what happens today, climate's an average. And so we're trying to keep our average not shifting too much over further. So why do we care about increased temperatures? When we think about different impacts, there's a number of ones that we can look at, but I wanted to focus on 5 specific ones that are relevant for Colorado in particular. And we think about extreme heat, poor air quality, wildfire, drought, and extreme weather. And all of these are actually interconnected. And when we think about especially extreme heat impacting air quality, wildfire impacts air quality, it really is, none of these are independent of the other ones. What I'm going to do now is just think about more of the health side of things and talk about extreme heat first and then come into air quality second. So how does excess heat harm health? And I'm going to, again, this is a medical school lecture hall, so I'm going to give you a little medical school lecture primer. So if we think about our normal body temperature, it's 98.6 degrees Fahrenheit. That's our core temperature. So what happens if we get hot, right? So we've all had exercise. I was in my garden, and you get sort of sweaty and flushed. And so you can have some excess heat exhaustion. For those who do running, they get heat exhaustion. But sometimes you can increase your core body temperature. And that can relate to other heat-related illnesses. And when we think about hyperthermia, it's when your core body temperature gets up to 104 degrees. And that's usually from sustained exposure to heat, where it doesn't get a chance to cool down. I get hot working in my garden. I come inside, take a cool drink, and cool down. But if you can't cool off, your body temperature can't cool itself. Eventually, it loses its capacity to cool down. So extreme heat that's uncontrolled, where people don't have the capacity to get to cooling, can affect to heat-related illnesses. And what we can see is we have risk of dehydration. You can get altered blood clotting. You can get airway spasms. And you get blood vessel inflammation and nervous system impact. So all of those are sort of consequences of heat-related illness, and especially thinking about in terms of stroke. Oops, went the wrong way. One too many. So when we think about, we were talking about social justice and thinking about populations that are vulnerable, we want to think about if I'm healthy and active and working and I have some heat exposure, that's one thing. But what if I have some underlying conditions, and how does that harm me as well? So people with kidney disease, oops, keep on hitting the wrong button. Sorry about that. There we go. I finally got it. All right. So people with kidney disease, in the context of heat, they can't maintain body volume and electrolyte balance. And actually, some of the groups within our consortium are studying chronic kidney disease of unknown origin and work on sugarcane workers in Guatemala and Central America, as well as evidence here within the San Juan Valley. If you have cardiovascular disease, you cannot sufficiently increase the blood flow from the heart to accommodate the extra heat. If you have diabetes, you can't properly regulate your temperature, so you've got issues with regulating temperature as well. If you have lung disease like COPD, you can't sufficiently increase your breathing rate to accommodate the extra heat. And there's actually certain medications that affect heat, antihistamines, some antipsychotic medications that affect your ability to regulate temperature as well. So a lot of people with chronic conditions have these additional challenges in the context of heat. So what I'm going to do now is just think about air quality and thinking about what can happen there as well. And we've heard a lot about this already today, and thinking about unhealthy air. We talk about CO2, ozones, aeroallergens, VOCs. What do they do in terms of health? We can think more of sort of lung inflammation, what happens to the lung itself when you're exposed to those unhealthy air, respiratory systems, asthma, emphysema, asthma exacerbation, premature death, hospital visits, missed school work days. We've heard about that already today. We can also think about the role in systemic inflammation and problematic in terms of those populations, blood vessel disease, non-fatal heart attack, irregular heartbeat, premature death in people with pre-existing conditions. And finally, also, we heard today as well about the effect on infants in utero and fetal growth restriction. So poor air quality does have an impact on health, as we've been hearing today. And we think about it in terms of Colorado, what's going on here. So we see increased air temperature, we see poor air quality, we see worsening drought, and more frequent and destructive wildfires. And all of those are affecting our health. And just to think about specifically for Colorado, Taryn already talked about this, but a typical Colorado summer day in 2050 will be similar to the hottest days in the past 100 years. One of the things to think about, just to put a scale on it, we've talked about the hottest days, the last 20 years have had 15 of the hottest days in the last 200 years. So the kids going to college right now have been born in a different climate than most of us in this room have experienced. And that's something for us to think about in terms of climate changes here and now in terms of that increased heat. And these kids are actually getting to college and being affected by that. Poor air quality. More than 3.5 million Coloradoans live in counties that experience one or more unhealthy smog days per year. Drought. 37% of Coloradoans currently live in drought, and 2000 to 2014 was the worst in 100 years. And then we have more frequent and destructive wildfires that Taryn had mentioned. 25% of the fires in Colorado between 1970 and 2012 occurred in the last 2 years of that period. And the annual acreage burned and increased by tenfold. So Jim Crooks, who's here, gave me this slide from National Jewish and Colorado School of Public Health. And we've been hearing a lot about PM 2.5, and again, I don't want to cut into the wildfire group, but I just thought this was a really nice representation. I keep on doing that, sorry. This right here is just looking at a map of Colorado with the levels of PM 2.5. This is sort of doing it over time from 2006 to 2016, and you can see the cyclic variation. But importantly, if you look in here at Denver metro area, the amount of PM 2.5 total versus wildfire, you can see that some but not all of these peaks are due of increases in PM 2.5 are due to wildfire. So it really sort of brings that link back to air quality as well. So if we look at groups at harm, one of the things to think about, again, as I talked about, is those with medical susceptibility, children and the elderly, the urban poor, those exposed to the urban heat islands, people with limited access to public health infrastructures, these cooling centers, as I talked about, if you can't get cool. Denver, my mother was born here 1922. Denver, that time period, nobody needed air conditioning back then. And there's very few houses in the old Denver area that actually had the air conditioning. What if you have that's where your populations are going and they don't have the capacity to cool off? Outdoor workers is another one that we really have to think about because the outdoor workers are exposed to higher and higher temperatures and not, again, the ability to cool off and also the poor air quality. So just to think about back to Colorado, how many percent of adult Coloradoans? By 2030, 18.4% of us will be older than 65. It might be sooner for me. And interestingly, this is most people older than 65 have some type of chronic medical condition. 2.5% of those actually have heart disease. And if you think about the number of children with asthma, 64,700, the number with diabetes, over 160,000, and COPD, those are real numbers of people here right now that are going to be susceptible to the health consequences of increased temperature and climate change. So I think it's good to bring those numbers back home and remind us that it's not sort of an abstract thing about where climate change is impacting, but in Colorado there's a lot of people that are going to have a higher risk and susceptibility. So what do we do about it? Because we're academics, we formed a consortium for climate change and health several years ago. This is a partnership right now with faculty within the CU campuses and the Colorado School of Public Health. And our mission is to address current and future health issues affected by climate change by bringing together a multidisciplinary team of clinicians, biomedical scientists, public health practitioners, epidemiologists, and anthropologists, along with atmospheric scientists and climatologists. So Colorado, one of the things for everybody here to think about, we have a really unique opportunity within the state. You can hear from the people at Colorado State, at Boulder, here at Denver. We've got an incredible wealth of people that are working together on this problem and willing to work together. I think the sunshine makes everybody in Colorado a little bit nicer. I used to live in upstate New York. People are crankier there when it's gray all the time. But importantly, we're coming together to look at a number of different things. We're developing educational platforms to try to teach the next generation of students about climate change and impact on human health. We actually have the first climate health fellow, an MD, Cece Sorensen. We're having a new one coming, she's in the emergency medicine department thinking about policy issues related to climate and health. We started the first medical school elective for fourth-year medical students, and we have a class for the MPH students. So really trying to bring that education. We're trying to work with our partners within the community, the state, and the U.S. To really bring our expertise to bear as needed. And importantly, we're also doing, because again, we're academics, we're doing research thinking about impacts of climate change on health. And I just have two examples here. John Adgate and Beth Carlton in the Environmental Occupational Health Department are looking at impacts of home energy efficiency programs on respiratory health among low-income residents in Colorado. And then Jim Crooks and Kathy James are looking at dust and asthma hospital visits in the San Luis Valley, one of our poorest areas within the state. Investigating how high levels of atmospheric dust increase hospital visits, really trying to get a sense of, in some ways we think about climate change as a force amplifier, force multiplier. It's not making new diseases, but we've got to understand what diseases are here, who's at risk, and how these changes are going to occur so we can help adapt and mitigate to those problems. So I'm going to stop there. This is a picture I took up in Crested Butte. This is the state we love during the wildflower season. And I'd like to thank all the members in the consortium who have helped educate me as we try to educate other people about, especially on the climatology side. We have two young students, Jake Fox and Cameron Newseminder, who are MPH MD students, who really helped put some of these slides together and represent the next generation working on this problem. C.C. Sorensen, who's our climate health fellow, Chris Karnakis and Jim Crooks, who provided some slides, and Kathleen Wells, who's with the Citizens Climate Lobby, and she and I have talked together about how do we bring this idea of public health and climate change together in presentations. So thank you.
Thank you, Rosemary and Taryn, both. And so if I might invite you back to the stage, Taryn. I guess that way you're both here and available for any questions from folks in the audience. Post-lunch thinking. All right, good.
So one of the things that the health effects that often gets missed, especially in air quality, is sort of foodborne illnesses. In terms of just food prep, what's safe at 80-degree outside ambient temperature is not safe at 85 or 90, and we're often. Do you have any thoughts on that, especially in a growing urban area where food safety and foodborne illnesses?
I'd say that's a great question, but it's not one we've really explored yet in terms of thinking about that. But it's a good point to bring that in, and as we start thinking about the impacts of climate change, all these different pieces you haven't thought about, right? And how do you bring that point in there is very important.
I would just add that there's been some studies on salmonella and increases in salmonella as a result of climate change. I think that's the area that we talk about the most as far as foodborne illnesses. Vector-borne illnesses are another component that we talk a lot about. Colorado's not primed for something like Zika right now, but we could be. Right, you could study malaria in Colorado. And again, even just exposure to things that we wouldn't necessarily be exposed to otherwise. In 2011, I got a call from the Commissioner of Agriculture saying we had some cattle die off as a result of anthrax poisoning. And it was one of my, come again things. And he was like, oh, yeah, it was just naturally occurring anthrax in the soils, but because it's so dry, they chewed down to the nubs and killed themselves. And it was just very nonchalant and matter of the fact. And as I started to look into it more, this is something that as we see increased occurrences of drought, things like that are going to become more and more common. And so we're starting to look at that as a result of climate change as well.
Yeah, thank you. My question is for the state, but whether DNR is interested in updating the global warming potential for methane. My concern is that the short-term global warming potential methane is understated. EPA is still using a factor of 36 over 100 years. Some reports do the 20-year, but I think logically we would also analyze the 10-year global warming potential of methane, which is about 125 compared to CO2. Is the state going to update that factor?
So this would actually fall under CDPHE because CDPHE does our inventory. And we are constantly looking at what information is available and how we can improve our data and tracking and inventorying. And you saw that one of the pieces of legislation had to do with tracking and climate data, which, we have our inventory that currently we update every 5 years. And so there's a really big lag in data and information. And so we try every 5 years to update that with the best available information. But we're really resource constrained on kind of what we can and can't do. But I think even though the new inventory will be coming out here in a matter of weeks, I think as we start looking at implementation of some of this new legislation and what that means for data and tracking, we're certainly looking beyond just CO2 and looking at how do we capture things like, do a better job capturing things like methane's impact and HFCs and all of those as well. So I think that's a conversation that we're going to be continuing to have.
Okay, we have a couple of questions from our remote participants. The first one looks like it's a bit of a trading question. So do you believe that we are at a point where it would be more beneficial for Colorado air quality to spend $1 in other states or countries where pollution is much worse and being transported into Colorado rather than spending that same dollar internally? Or maybe we'll just have John take it.
Wow, that is a packed and layered question. I don't know that there's been any cost-benefit analysis on that. I would be fascinated and interested to see some kind of study on whether or not that would be, from a climate standpoint, be more impactful. But what I would say from a local air quality standpoint is that there are co-benefits that exist to reducing things like, the precursors to ozone, also reduce greenhouse gas emissions, but the benefits that we get at a local level from a local air quality improvement are really, really important. And so I think focusing on that component for Colorado, we don't want to lose that piece of it just because we may not be the largest emitter of greenhouse gas emissions. There are plenty of greenhouse gas emissions that need to be reduced. We really should just kind of reduce across the board, I think.
Okay, great. And then the next question is, since emissions have no boundaries and circulate along the Front Range, how do we regulate sources of emissions in municipalities or counties that are known emission centers? Not sure. That's a climate question.
Is that, that's, I could interpret that in a whole different host of ways. I'm going to take the least politically contentious route. So I think, again, climate change, the solutions to climate change, we know how to address this issue, but it takes all hands on deck. There is no element of Colorado's economy and no corner of our state that is not impacted in some way, shape, or form by climate change. And so we really need to take a comprehensive, multifaceted approach to addressing it. And yes, there are things that we are doing to address kind of the largest source of emissions. We're looking at our power sector. We are working with our utilities. We are looking at how we move people and looking at multimodal transit. We are looking at our built environment. We are looking at how we regulate the oil and gas industry and the methane emissions that come from those industries. And so we are looking at sources of HFCs and the whole short-lived climate pollutant package. And so we are really trying to be comprehensive. I don't think it necessarily does us a lot of good to point fingers and say, you're emitting more or you're emitting more from a regional standpoint. I think just finding our sources of emissions and trying to reduce them across the board and really focus our attention where we get the biggest bang for the buck is the most important. And the other thing that I would add is that we are collaborating. We get that emissions know no boundaries, and so we are part of the U.S. Climate Alliance, which is a consortium or an alliance of now 22 states and the territory of Puerto Rico that are committed to upholding the reductions under the Paris Accord. So 26 to 28% reduction in CO2 emissions under over a 2005 baseline. And so we are working with our partners to address this across the nation because we understand that this is not just a Colorado issue. This is a national and global issue.
Great. And one last question.
Lisa McKenzie, Colorado School of Public Health. Hopefully this is an easy question, not political. I'm just wondering if anyone in your consortium is looking at the probability of increased dust events with the droughts and that influence on air quality.
I should ask Jim Cruikshank right there. So yes, Jim is looking at that, and he'd be happy to. Do you want to speak to that, Jim?
I don't think anyone in the consortium has yet done a prediction of future dust storm emissions. There are certainly members like me and Kathy James and Matt Strand. I know Kathy and Matt did this study in the San Luis Valley looking at data from the past decade. I don't know that they've gone and tried to predict future, future health impacts based on future dust emissions. But that's certainly a really interesting idea. And I have a tiny little contract with the EPA to look at effects of dust storms on ICU admissions for cardiovascular and respiratory disease. So I'll let you know the results of that when I have them. Thanks.
And then I would just add, from a mitigation standpoint, we're working with the ag community on soil health initiatives and cover crop initiatives to try to reduce the dust storms that we see during drought events. And so it would be interesting to couple that with your study as well.
All right, let's thank our speakers. Okay, so next on the agenda is a break, and it's a bit of an extended break, but I hope we don't lose you because our last session on wildfires is going to be really interesting. But use this opportunity to grab a cup of coffee, network with some of the brilliant people who are in this room, and we'll see you at 3:30.
Yeah. All right, so we're into the final session here, and this is going to be on wildfire smoke, which I think anyone who was in Denver last summer knows this is a very relevant topic, and we have two great people to talk about that. So Emily Fisher, who's an assistant professor at Colorado State, an atmospheric scientist, and her team carries out studies of wildfire smoke and makes measurements during fires, as well as interests in climate change and sustainability.
Is the microphone on now? Awesome. Thanks so much for having me. I'm here to give you a smattering of wildfire-related research from my group and some others at CSU, and then I'll talk to you about a major field program that we ran last summer to study the chemistry of wildfire smoke. This one. Which button? That one? Yes. All right, so let me just go over a few recent papers from my group on wildfires, and I mean this for the commission just so that you understand that I'm happy to serve as a resource on this topic moving forward. So large wildfires account for most of the burn area and thus emissions in the western U.S. This is a map of the FPA FOD data set, which goes back to 1992. And so these are all wildfires that occurred in that time, and then the color tells you how the fire was started, whether it was a lightning ignition or a human ignition. So the West, unlike the southeastern U.S., most of our fires are large, and about 70% of the burn area is attributed to human ignition. Sorry. So in my group, we've been trying to teach ourselves as much as we possibly can about fires on a variety of different timescales. And so one study that we just finished up looked at a bunch of different ecosystems in the West. So that's what the map shows you here. I don't dare do the laser pointer, right? It's better for cats, but it's kind of high. So there we go. So the forested mountains, high desert regions, and Mediterranean California. And so we're looking at the past relationships with meteorological drivers. So for here, temperature, precipitation, and relative humidity, and looking at how they vary on a summer average thing. And so what we were looking at here was whether human and lightning-ignited wildfires vary similarly with environmental conditions. They do, and sort of the implication is that as climate changes fires, climate will change both fires that are ignited in both ways similarly. We're working on now examining the spread in environmental conditions moving forward with climate change that may drive future burn area. So I expect that we'll have a paper on that by the end of the summer. It's done, and as it turns out, I know these slides are getting posted, so not to stress out my grad students, I didn't want to post them online. But for some of the ecoregions, temperature is a good predictor. It's what we know best moving forward, but for some of the different ecoregions, it's not the best predictor for wildfires if you look in the past. So let's focus in a little bit on air quality. So we've been looking across the entire U.S. at how many days during the fire season you can see smoke from space, and that's what this blue color shows here. So that shows you the average number of days that an analyst working for NOAA sees a smoke plume overhead from satellite. And so for Colorado, if you just look in there, that color, that's about 5 or 6 days per month during summer. You can see a smoke plume from space that's large enough to see from space. And then about 50% of the time, ground level PM 2.5 is one standard deviation above the mean is what I have shown here. So that's a sort of that sort of gives you a sense of, in Colorado, how frequent we're seeing smoke on the ground that is noticeably above the sort of average. Just to think about fires in Colorado, air doesn't know borders. So the northwest and the southwestern regions of the U.S. export a lot of smoke to Colorado, and I think that's what you were referring to from last summer, right? So as I'll talk about later, I was not here during that time. But we've been looking at these sort of long-term data sets of fires, looking at their distribution in time and running, Rosemary, it's hard, I know, this thing. So we're basically running atmospheric transport models forward from every fire that's burning in a given summer and seeing where that smoke goes. So we can understand now which locations are more susceptible to other regions that will be burning. So in Colorado, for example, roughly 2/3 of the time when there's smoke in Colorado, the smoke did not originate in the Rocky Mountains. It originated either in the Pacific Northwest or the southwestern U.S. So this is a nice paper by Kate O'Dell. She's a graduate student that I co-advised with Jeff Pierce. And so what she did was break apart PM 2.5 trends for the entire U.S. into a non-smoke fraction and a smoke fraction. And she did that in 2 different ways. She did it one way using visible satellite imagery, and another way using a chemical transport model, which is which is geochem. And so if you look over on this side here, this is total PM 2.5. That's a trend between 2006 and 2016. And you can see like this beautiful blue over here, right? There's been strong improvements in air quality in the eastern U.S. And then look over here, right? You don't see the same blue trend. And so the same blue colors, rather. And so she broke that apart, and what she's finding is that both the model and the observations seem to indicate that even these sporadic smoke events are starting to offset improvements in the mean air quality in some regions. And there's another nice study from the University of Washington out of Dan Jaffe's group looking at the 98th percentile, and you see the same story as the mean, basically. So we've been looking, this looks funny, but it was made on a Mac, so that's probably why. So we've been looking at ozone in addition to PM 2.5. I've actually been working very hard to try to understand how ozone is produced in wildfire plumes. So we've looked between 2005 and 2014. This study came out in 2016, so that's why we ended there. Looking at the number of days that a site has MDA greater than 70 ppb, so that's the size of the dot here. Sorry, there we go. It's the size of the dot here. And then the color indicates the percent of the time when you had a day greater than 70 ppb that smoke was likely in the atmosphere. And so this color for Colorado, I know it's very hard to see, is sort of in the relatively low, so the purple and blue in Colorado, because we ended the study in 2014. There would be we probably would have a little bit of a warmer color there if we had included the last couple years, but I'll talk more about that. So in 2015, we were actually working on oil and gas, trying to understand the chemistry of what happens when emissions from oil and gas activities intersect with the urban sources. But we had these enormous smoke events, right, in 2015. And so here's just a time series of PM 2.5 and carbon monoxide. And you can see these red is when these sort of large smoke plumes came from the Pacific Northwest. And so what we did with that was look at how ozone changes under those conditions. I want to point out, I'm in the fire session, right? So I don't want you to think that I think that fires are the only cause of poor air pollution. So this is a time series of max daily hourly ozone, and this site is the BAO tower, which has been taken down but was by Erie. And this is max. So this is max daily ozone. This is the 95th percentile, and you can see that there were several elevated ozone events that occurred during the wildfire smoke period. It was very cold here. This is temperature on the bottom. But then we also have a paper on these sort of elevated ozone periods that are homegrown or are clearly anthropogenic pollutants. And that paper talks about sort of a chemical signature of alkanes contributing to the ozone production. So what we did, and one way that we're studying this, and then I'll talk a little bit more about other ways we're studying the ozone, is so here's ozone on this axis, here's temperature. Ozone has a positive relationship with temperature for a variety of different reasons. But if we break the summer 2015 apart into different periods, so the smoke-free period, ironically here, is in gray. The August smoke period is in red, and the orange smoke period here is the July. The orange is the July here, and you can see that for a given temperature bin, right? So if we look between 20 and 25 degrees, the mean amount of ozone that was in that air mass as compared to the rest of the summer was quite different. It was between 10 and 12 ppb. So I'm working on trying to understand how smoke produces ozone, whether that's a fast process, whether there's a slow process, whether it's enhanced when smoke mixes with an urban air mass. Questions like that I think we still need to answer. So this is how I spent last summer. So last summer I had this awesome opportunity to lead a very large team across 5 different universities and NCAR to take the NSF NCAR C130, which is, if you know, is based in Broomfield, so just a really wonderful resource. So we actually put the most instrumentation that's ever been on the NSF NCAR C130. I did not know that when I started planning. But and we took the aircraft to Boise, and then we flew in 23 different wildfire plumes. And so these are some photos that I took from doing that. And so basically what we would do is we would go out to a fire. Let's use the car fire for an example. We'd go out behind the fire, and then we'd zigzag the plane down in the smoke. And so I'll talk about the kinds of things we were measuring in a minute here, but just to let you know, this data set is coming, and so we should know a lot more about smoke chemistry within a year. So we also sampled, I ran a class at the end, so I also sampled the prescribed fire that occurred in September by Red Feather Lakes, and then the Silver Creek fire, which was that big wall of smoke that we saw in September here. So we did that with students. It was fun. And I don't usually get to credit John Volkins for my logo here, but it's really, he inspired me to do that. Okay, so what did we measure during WECAN? So we took the C130. We actually focused on 3 different topics. So the first one is nitrogen emissions and evolution. That's essential to understanding the ozone production in wildfire plumes. And so that's really my focus. And also nitrogen deposition to ecosystems. We also were focused on the evolution of aerosol optical properties. So I come from an atmospheric science background. So smoke in the atmosphere is interesting for many reasons, in addition to the air quality impacts. So there's radiative impacts. You might think about that as what's the impact on crops underneath when there's smoke aloft. And then we have a group at CSU who's interested in cloud activation and chemistry. And so what will happen to storms in the West as we have more smoke around? So what did we measure? I have this up here just quickly so I don't forget to tell you something. So we measured a lot more things that are measured at a surface monitoring site. So a full, almost nearly comprehensive for the nitrogen in the plume, so NOx, ammonia, pan-nitric acid, isocyanic acid. We had 3 different ways of measuring VOCs, and so one thing we're working on now is taking our measurements of aerosol size distributions, so what is the size of the particulate matter in the smoke, and ratioing that to the different VOCs. So, like this, if you had 25 micrograms per cubic meter of smoke, how much benzene is there as well? So we can answer questions like that. And that's something that we're trying to do with the data set. And those of you from the health community, if you could tell me what you want to know about if there's so much PM2.5, how much acetaldehyde, how much formaldehyde, I would like to tell you that, and I can tell you that. We're working on how to just describe that to everyone. So in addition to sort of systematically sampling smoke very, very close to the source, we actually we surveyed mixed-stage smoke covering really large regions. So I took a flight down into the Central Valley when the Central Valley had smoke from the Car Fire, the Mendocino Complex, and the Donnell Fire all pummeling into the Central Valley. That's sort of a picture of what that looked like. And then we did some large surveys when there was smoke pouring from Oregon and California out this way, and there's just sort of, I call it a river of smoke. Basically, it was everywhere. So that's more analogous to the chemistry of the smoke that might be coming here after a few days from those regions. So I think we'll be able to sort of apply some of that. We have 34 ascents and descents in and out of Boise. And so we can sort of, I'm hoping to have a summer student do this summer, divide that data set into clean days versus smoky days, so we can start to understand how the, I know that this Boise is no Denver, but sort of how does that change with and without smoke, because they do get hit a lot, and I think we can learn a lot from that data set. And then we had some student-led educational flights at the end. So I taught a class across CSU, University of Montana, University of Wyoming, and North Carolina A&T. And the students did a bunch of fun things. We sampled feedlot plumes. We went up to the Rollins refinery, and we sampled the prescribed fire and the large local wildfire with a reduced payload. But lots of interesting things in that. So anyway, I'm happy to answer any questions about this. I'm glad that I have Colleen here so that she can talk about health and I can talk about gases, because I don't really understand how things that are alive work. But there's a lot of information about this field project. The data, most of the data is final at this point. It will all be public in September, and collaboration on this is very, very welcome. And if there are questions that you have, I have a very rich data set about smoke, and I'd be happy to probe that data set in any way that was meaningful to this community.
We'll do questions afterwards, so let me introduce you. Okay. Final presentation for the day, but we'll take questions for both of the wildfire speakers afterwards. This is Colleen Reed, who's an assistant professor at the University of Colorado, Boulder. She's trained in environmental health science and population health, and also has an interest in wildfire smoke and climate change. Thank you.
Thank you. Okay. Can you hear me up at the top? Great. Well, thank you so much for having me here. As he said, I am an assistant professor in geography at the University of Colorado Boulder, yet I was trained in environmental health sciences. And one of the main lines of my research is estimating population exposure to air pollution during wildfires and linking that to administrative health data sets to better understand and do the epidemiological analysis to better understand the relationship between air pollution during fires and health impacts. And so that's really, I'd say my strength is more on the health impact side. And so similar to what Dr. Fisher was saying, I'm really excited to collaborate with anyone who's interested in understanding how the air pollution is linked to health. And we have lots of experts in this room on that too. So I don't think I have to spend much time explaining to you why it's important to study wildfire smoke in Colorado. And obviously Dr. Fisher just did a great job explaining that. This is just a satellite image where they drew the polygons, which is one of the data sets that Dr. Fisher was talking about. Showing, this is from 2017 when there were a lot of wildfires in the Pacific Northwest that were affecting air quality in Colorado and throughout the United States. But just one thing to point out here is that I'm going to be, one of the reasons that I put in this slide was to remind myself that the work that I'm going to be presenting on today is sort of a synthesis of the epidemiological literature on the health impacts from wildfires, and that comes from studies done all over the world. There's actually a large group studying this in Australia and in Europe and in Canada and here, and so most of the studies are not actually specifically focused on Colorado. There are a couple of studies that have been done on wildfire smoke in Colorado and its health impacts, but there needs to be more of that done. Particularly as I get into this further, I'll talk about the fact that at this point in time we don't really understand how smoke from different types of fires might impact health differently, and or the underlying health of the population being exposed might also be related to the findings we find in these studies. I don't think in this room I need to spend too much time talking about all the air pollutants that are emitted from wildfires, but when I give this talk to I was asked to give this talk to mostly medical professionals, and I needed to talk more about the air pollution side. Versus I'm going to spend more time on the health side today, because all of you know that. But one thing to point out is that most of the literature on the health impacts from wildfires is focusing on particulate matter, not any of the other air pollutants that are part of the smoke that people are exposed to. And there's a few reasons for that. We know that particulate matter is quite high during wildfires. We also know that particulate matter is very important for health. It's also measured, right? It's very easy to get the monitoring data for particulate matter versus not as easy to do so for, say, PAHs. But ozone is also measured quite a bit. But similar to what Emily was pointing out with her studies trying to understand ozone formation from fires, we know that some fires are creating really high levels of ozone compared to the background levels, and some are not so much. I am not presenting it here, but I do have a paper that was recently accepted. It's not yet online. That hopefully I'll be able to get that to you soon, where we were for one specific fire in Northern California in 2008 compared particulate matter exposures and ozone exposures and how those related to respiratory health. And for that fire, we saw that both air pollutants were elevated, but the PM was about 6 times the background levels versus the ozone was maybe, 10% increased compared to background levels. And so not surprisingly, the health impacts was mostly driven by the particulate matter. But that doesn't mean that a different fire wouldn't have different results. And so it needs to be studied further. Before I get into what we know about the health impacts from wildfires, I'm just going to talk about some of the challenges in studying this from an epidemiological perspective. One of the challenges is that we never know when a fire is going to happen. So it's normally after a big fire. Everyone's asking the question, okay, what was the health impact from that fire? And so to study what the health impact was, we have to turn to data sets that are regularly collected. And so when we do that, we are often looking at deaths. Deaths and hospitalizations, which is the proverbial tip of the iceberg. And that's what I like to show about this pyramid. Think of it as an iceberg. And so if we think about the population that's exposed to the fire, say everyone in this room was breathing in really high levels of air pollution from a wildfire, all of us would probably have some sort of subclinical effects, but we wouldn't necessarily know them. We might not have any symptoms that we would observe. So we're definitely missing all of that down here, and that would be sort of everyone exposed. A smaller subset of everyone exposed might start to exhibit symptoms that they would notice. They might have an increased cough, itchy, watery eyes. Maybe if that person was like me and has asthma, they might use their rescue medication more. But it wouldn't get recorded in a system that we could then analyze and see if that was a health impact, unless they used the medication so much that they needed to go to the pharmacy and refill it, or needed to go back to their physician and get a further prescription. And so most of the time, the data that we're looking at are deaths, hospitalizations, and emergency department visits. There are some studies that look at physician visits and or renewal of prescriptions, but for the most part, we're looking at data sets that are just the most sensitive individuals that maybe already have pre-existing respiratory health concerns and or are just more susceptible to that exposure. And so I'm going to be highlighting 2 papers that I've led that summarize the literature. One came out in 2016 that I did with collaborators in British Columbia and California, and then one that I've done more recently with Melissa Mestis, who's my postdoc here, where we were looking just at the respiratory health impacts versus the first one we looked at all health impacts. And so the one takeaway I want you to take from today is that we know there's an association between wildfire smoke exposure and respiratory health. Almost every single study that has looked at asthma exacerbation, so that means that someone who is experiencing an asthma attack and maybe is going to the emergency department or so severe that they get hospitalized, that we see increases in ED visits and hospitalizations for asthma when there's really high smoke in almost every study. Similarly with chronic obstructive pulmonary disease, which you can think of as emphysema, is associated with wildfire smoke. And then there's growing evidence of wildfire smoke being linked with respiratory infections such as pneumonia and bronchitis. And this is levels of pneumonia and bronchitis that get to an emergency department or a hospital. With cardiovascular disease, the evidence isn't as clear. Almost all of the studies on wildfire smokes to date have shown no association. However, there's a few more recent studies that have found significant associations, and it's unsure why there are differences. And this is really important to point out because there's this large literature on particulate matter from other sources affecting the cardiovascular system. And I put on here this diagram that really outlines that we know so much about how breathing in particulate matter can affect the whole body and the cardiovascular system. And so I'd say before these more recent studies, some hypothesize that the reason there wasn't this association was that wildfires are really large exposures, but for a short period of time. And therefore, if you could survive that period of time, then you might be able to recover. However, some of these recent studies have only looked at one wildfire season or a specific wildfire event and found some significant associations. And their hypothesis has been that they are, some of those studies have hypothesized that it's due to being very specific about what health endpoint you're looking at related to cardiovascular disease rather than lumping them all together. So there's been some studies out of Australia that found it for out-of-hospital cardiac arrest, and then, but then there was a study that found for just people over 65, so maybe looking at specific air quality levels. There needs to be more research to understand these differences across studies because it could be that it's due to the actual chemical composition of the smoke. Different fires might be producing different toxicities. It's also possible about the actual levels of air pollution exposure and the duration of the event. It also could be the underlying health of the population. So one of these papers is out of the southeastern U.S., where we have much higher rates of cardiovascular disease prevalence than we do in the western U.S. We need to do a lot more research on that. There have been a few really good studies that have found a link between wildfire smoke exposure and all-cause mortality. These have been in cities that are impacted by wildfire smoke repeatedly every wildfire season, one coming from Australia and a couple of studies from Europe. As of yet, because death is such an extreme health outcome, there's so many fewer that happened. Yes, okay. It's at the top of that pyramid. That's what I mean by that. You need to look at these cities over long periods of time to have enough statistical power to find that link. And so as of yet, we don't know what causes of mortality are impacted, just that there is this signal with all-cause mortality when you associate it with smoke. There's been not much research on wildfires and birth outcomes, despite the very large and growing literature on other sources of air pollution and birth outcomes. There's a paper that I'll highlight here that I was involved in. It came out quite a while ago, where we looked at the 2003 fires in the South Coast Air Basin of California. So that's the Los Angeles area. And we looked at births that intersected with the wildfire event temporally and compared them to births in the same population, so the South Coast air basins that were delivered before or conceived after. And we found a very small but significant decline in birth weight that when averaged over the whole population can be very meaningful. We know that birth weight can being born low birth weight can impact health throughout the life course. And so this is an important finding, but needs to be followed up with other studies. I think mental health needs to be studied a lot more. Most of the studies that look at mental health impacts of wildfires find that people who have been evacuated, lost property, or lost a loved one are more likely to experience post-traumatic stress disorder or depression. However, there's also been at least one study, it was a qualitative study in Canada, that found that people just exposed to smoke for a whole summer were experiencing some significant mental health impacts. It was a First Nations community, and the smoke existed for the whole summer such that they felt that they couldn't go outside. There was less interaction with their peers, less engagement in physical activity, and many people reported just from smoke exposure some mental health impacts. And if you think about, in Colorado, I was thinking about this, with so many people who love the outdoors and exercising outdoors. If the smoke is so bad that the warnings are don't engage in physical activity outdoors, if that were to happen on a regular basis, you could imagine that there could be mental health impacts. I'm always interested in which populations are more susceptible or more vulnerable, and the literature to date on this for wildfire smoke is not consistent. There's some studies that say that find that people over 65 are more susceptible. There's others that find that working age adults actually have a more significant relationship with adverse health impacts from the smoke. The clear evidence is anyone who has asthma or chronic obstructive pulmonary disease is more likely to be impacted by these high air pollution events. There's been very little research on differences by race, ethnicity, and the evidence so far on socioeconomic status is interesting. It's not consistent when you look globally. When you look just within the United States, almost all of them are showing that people of lower socioeconomic status are more have more health impacts from wildfire smoke. And this is interesting because air pollution from wildfires is not sort of as socioeconomically patterned as it is when you think about traffic exposure or exposure to point sources that can often be cited in lower income areas. And so the air pollution exposures may not be different, but the health impacts might be. And that's, I think it's an important thing to consider. So I'm going to leave you with a lot of things that still need to be studied related to wildfire smoke and health. And I'd be happy to talk to others about a way to do this. I look around the room and I see lots of other people who study this too. So there's a growing group of us in Colorado. I'm often asked, what's the long-term health impact? Say you were exposed to a very high air pollution event, or someone might ask, like, my child was at this really important stage for growth and development, and it was exposed to this really high level. What's going to be the impact on their lung function long-term? And unfortunately, at this point in time, we don't really know. There's one study out of Indonesia that finds that that men who were exposed to the 1997 wildfires had declined lung function, 10 years later. But they didn't find, but that's just in one context and needs to be studied in other contexts. There's lots of other health endpoints that haven't been studied related to wildfire smoke that have been studied from other sources of air pollution. So there's growing evidence of a lot of other health impacts of air pollution that need to be studied with wildfire smoke. As I said before, we need to look into why we're seeing these different findings for cardiovascular disease in different studies. There's lots of possible reasons, and I think understanding why would be really informative. We need to look at other air pollutants, not just particulate matter. So as much as I said we need to look at ozone, I think it's also important to look at other gases as well. We need to look more into vulnerable populations. And then I was just talking with someone from CDPHE about this. We often tell people during a wildfire event to shelter in place or not engage in physical activity, and there definitely needs to be more research into how effective that messaging is in terms of people changing their behaviors, but also whether or not that's actually causing people to not need to seek medical care for respiratory or other health impacts. And so with that, thank you very much. I'm happy to engage questions and also get to know all of you and collaborate more. I'm very new to Colorado and really excited to get involved in research that's focused on the population and health here.
So very interesting. I can tell you anecdotally, almost all of my patients will complain of worse symptoms in wildfire. So, they don't elevate to the level of being in the hospital. They're at the bottom, in the middle of that pyramid. But I had a question maybe for both of you with the composition of the materials that were in the fire versus maybe what's known about the geography of the fire. So some fires are really confined to the wildlands, but there were a lot of fires last year which burnt cars, or all the images of liquefying cars. And you can imagine that the toxicity from one which spreads into an area where there's a potential to incinerate, non-biomass material might have just a whole order of magnitude of toxicity more. Is that something that, I know you mentioned the heterogeneity in the results, and that's one obvious area of heterogeneity in addition to what's burning. Is that something that maybe will be teased out in your analysis, or both?
You can do air quality on the help.
So we have, we have one wildfire that I'm sure was burning structures. So that was the car fire. We were there the day that the fire tornadoes happened, so about 2 hours before that. So we're looking into whether the VOC composition differs in that wildfire. We're probably not going to be able to tease it out. sadly and awesome, next summer, they're gearing up now. There will be a similar study to what we did that's organized by NOAA and NASA, and they will be a little bit more intentional about that if there is, to get more about the composition. If there is an opportunity where structures are burning, where non-wildland is burning, that will be one of the things they'll try to sample.
So my research group has applied for funding to try and analyze that. We're really interested in the question of whether or not the health impacts are different for different types of fire in terms of whether it's a peat fire or a grassland fire or what we're calling sort of an urban invasive fire, right? It's starting in the wildlands, but it's going across this urban area and burning lots of structures. And our hypothesis is that the chemistry would be different, but would the health impacts be different? And that's sort of an open question at this point.
Let's see. I noticed that when you have flooding on burn scars, you often get high levels of mercury that come off the water column and come down into the rivers and streams. I was wondering whether you see levels of mercury in the smoke emissions.
We did not sample mercury on our aircraft. Okay. So, yes, you can see elevated mercury in other studies that I've been involved with but mercury is not my specialty, but I've worked at sites where they've been also measuring mercury. So yes, and I did not do it this summer.
Okay. Thank you.
It's Auden Schendler from the Air Quality Control Commission. Is anyone studying firefighters? Because it's crazy being in a town near a fire. Those guys go out there and then they go to the next one and go to the next one. And then my other question for Emily is, do you have any hint as to the process that's causing ozone to increase?
Yeah. So yes, there are research groups that are investigating wildland firefighters and the health impacts on them. That's not what I study. But there's definitely impacts. I mean, one thing is that you have this very healthy group of mostly young men, some young women who are fighting the fires, but we do see, the studies that have looked at that do see impacts on their lung function across the season. But in terms of the long-term impacts, I know some researchers who are trying to get at that question, but John might know. John would know. No? Okay.
This is a historical note. John Peters, who actually started the Children's Health Study when he was in Boston, did long-term studies of urban firefighters, and not too much turned up. And there's interesting exposures. When I was at Johns Hopkins, we worked with Anne Arundel County and others because Baltimore Gas and Electric had nicely given them waste transformer oil for test fires for training purposes, meaning they were getting to inhale incinerating PBBs and other kinds of things. And there have been other studies. We looked at this, actually. There was a lot of interest because there have been cohort mortality studies of firefighters, again, all urban, and they've all been too small. And at the time, with this interest in sort of national interest in the firefighter problem, Barbara Mikulski, our senator, tried to get through some money to do a larger aggregated study that never happened. It seems like some of our new tools, like metabolomics, for example, would be something that could be very helpful for studying the questions, for example, that Tony got at, which is what are some of the exposures that might come with burning houses, cars, or whatever. I mean, there's obviously a lot of toxic materials being generated with burning plastics and electronics and whatever else. So we have some tools, and I actually don't know if they've been brought to bear, but they certainly could be with some prospective thinking about sort of before and after blood draws, just for example.
So to get to the ozone question, where should I start? So there is one mechanism that we've known for a long time whereby fires produce ozone. So What I observed this summer was a big surprise to me, actually. And I think part of this is that very few people have gotten this close and measured smoke that's so fresh in sort of a big wildfire situation. So in the first 30 minutes to 4 hours post-emission, if a fire plume is injected relatively high in the atmosphere, which the big fires are doing in the afternoon, we'll see dilution-corrected ozone production rates that are 100 ppb an hour. They're very, very fast, and so I'm not able to reproduce that with a chemical model. So if I take everything we're measuring, all of our VOCs and the amount of NOx, and even the sources of OH that we know about, which is the oxidant that's driving that chemistry really fast, I'm not able to reproduce that ozone production. So I'm actually working on a paper right now to sort of make a call that, like, the ozone is happening, ozone's being made in some of these fires super, super fast, and we might never be able to measure all the chemistry that's occurring. Now, there's another stage of ozone production, which is longer, slower, and further downwind. As those plumes descend, they might actually heat up as they go to lower parts of the atmosphere, and then some of the NOx that you had locked up in an organic form will be released, and that'll trigger, I think, another stage of ozone production, which we have observed many times. So the sort of really fast, I don't think we had observed before. They had in Africa, maybe a few studies have seen it, but then some of this longer term slow we had observed as a community in the past. So one thing that I really hope that they'll spend time on this summer is, and I hope they get I don't hope they get an opportunity, but I suspect they get an opportunity, and I hope they can take the plane there when they get the opportunity. Let's say it that way. So is when smoke hits an urban area, Seattle, California, go into that urban area and try and understand why there's enhanced ozone there. So we didn't do that. There was burning that was impacting Seattle during the time, but we were worried about being able to get into the Seattle airspace and do anything constructive with the plane in terms of the sampling. But I hope that these teams this summer can get at what happens when smoke impacts an urban area. And whether, it probably depends on whether that urban area is a VOC or NOx limited, or how that plays out. But I think that we should, between what I saw and what they should see this summer, I would bet in a year we know a ton more about that for air quality models.
So, Elise Jones with the AQCC. Emily and I got to talk a little bit about prescribed burning over lunch. Being from Boulder County, we care deeply about fire mitigation strategies, and prescribed fire is certainly one of them to try to reduce the catastrophic wildfires. So I was just curious whether or not what you understand about the health impacts of wildfires. Is it linear? So you do a prescribed fire, low-level burn, not as much, or is there some sort of threshold effect? And also then, this is sort of the question I asked Emily, has there been any cost-benefit analysis about trying to validate the use of prescribed burns to prevent, recognizing it has an air quality impact in the short term, but to prevent larger air quality impacts from catastrophic wildfires that ever been looked at? Two-part question.
Is it okay if I go first? All right.
You can go all.
So in terms of, well, I think there's two aspects to the health impacts of prescribed fires, which you mentioned there. So when you're asking about the dose-response curve and whether it's linear, and in the studies that I've done and tried to investigate this, we haven't seen, for respiratory health, we have not seen any deviation from linearity, but it also is, almost all of the studies assume linearity in the way they do the modeling, and so I don't know if higher-powered studies that might be able to discern the shape of that curve better haven't, at least they haven't published anything trying to discern the shape of that curve that I've seen. But I do think that there does need to be more research into the question of the difference in health impacts between prescribed burns and wildfires. And this is another area that my group, we've been trying to get funding to answer that question, because there are a bunch of studies that look at the air quality impacts from prescribed burns versus wildfires, and there have been a few toxicology studies that have taken smoke from prescribed burns and wildfires and looked at the differences in the impact. And sometimes they do see differences in the toxicology on sort of animal models or cellular models, but it hasn't been empirically analyzed at the population scale in terms of epidemiological studies. And so it's possible that the actual chemical composition of the smoke is different, and as well as the concentration levels. So I do think that we need to do some studies that, in addition to trying to understand the dose response curve shape and trying to see whether it deviates from linear, although I don't think there's not much evidence of that to date. But just to see if there are different, if you see health impacts from the prescribed fires versus the wildfires. And in talking to set up this grant proposal that we submitted that didn't get funded, but we're trying again, we've been partnering with the Westar air quality managers for the states in the western U.S., as well as the members of the public health departments of the states in the western U.S. about this question, and everyone seems really interested in it. But to date, there hasn't been any studies that I know of looking at the difference.
Like I told you at lunch, I think that's a great question. Just to follow up for everyone else on some other things to think about, so the fires will burn at a different temperature, a different moisture, a different meteorology. So who will get exposed, how long, where the plume will go will change. And so some of the sort of climatological work that we've done on wildfires, you wouldn't necessarily think that the prescribed fire smoke would go to the same place, right? Or so for that reason, in addition to how does the composition change, the way the smoke will move in the atmosphere will be different. So there's actually a lot there.
Rob McConnell from Southern California. So I have a question for both of you. You mentioned that you showed one of you referred to like a river of smoke and showed a plume going across the country. I wonder if do you have any data to look at how the composition of the plume changes as it goes downwind?
Yep, that's exactly what we're doing right now. We're doing aging. So with the WeCan data set, we had a lot of fires where we went very close, and then basically I could not get the plane out of smoke this summer. There was so much smoke everywhere. Yeah. And when I mean rivers, I mean like if you are looking, I have a LiDAR, so I can see below and above these like filaments. There's just rivers of smoke everywhere in the West. And so we flew in and out of them all summer. So we're dividing that into sort of young, medium, and old. Yeah. And looking at how sort of the benzene to PM2.5 versus acetaldehyde to PM2.5 versus formaldehyde to PM2.5, how sort of these VOCs that we know are hazardous, that piece we're working on right now, how they age. And there are differences with age, but I don't have the full story for you.
That's very exciting. And among sort of the many designs, the many health designs that you're thinking of, I mean, it would be really interesting to look at the sort of the smoke, thinking of PM as a marker, or the smoke effects of fresh smoke, medium smoke, and sort of across the country aged smoke, whether you see different coefficients of effect.
So where I will be able to end, I hope, is I can say right now we already make maps of what we think is smoke PM2.5, and we pass them to Jim. I pass them off to somebody else. So I'm hoping I can take those maps of smoke PM2.5, and then I can say, okay, well, if the PM2.5 was this, and it was approximately this old, based on the climatologies we have of smoke, then there was roughly this much of these other things were there when the smoke was there. So I would like to know from you and anybody else, what other VOCs other than the hazardous air pollutants that I know of would you like to know about? Because we can post-calibrate the VOC measurements for a variety of different things if there's other things of interest.
That's really exciting research you guys are doing. That's really nice.
And so this may be a good segue to maybe our last question, which is from a remote participant, which is, do you know of any research that has investigated the transport of ozone precursors from wildfires and the formation of ozone downwind?
Yes, that's what, and so That's what we're doing with the data set we have now. But the sort of order one operation is understanding the nitrogen in the plume, because that's key to how the ozone is made. So we're working on that from a chemistry perspective now, and then we've done sort of more of a geography style analysis, a spatial analysis of when you have smoke in the atmosphere, and you compare that data set to the same exact location without smoke in the atmosphere. On average, how does ozone differ between those two data sets? So we've done both of those things. One's been published and the other one is not. On average, mostly when there's smoke, then there's a little bit of an ozone enhancement in an urban area. That's speaking very broadly. We've done it for all the EPA sites across the U.S., but in general, that's the case. It's small and it varies quite a bit between site to site.
All right. Well, let's thank Emily and Colleen. And then I'm going to turn this over to Tony and John to do just some closing remarks before we end the day.
So I wanted to thank everyone for coming, and it's, I think, very informative for the commission. And then, my day job is mainly as a researcher, and the amount of expertise in different aspects of air quality, ranging from monitoring to the transport of across states of wildfire smoke, wasn't a goal of this symposium to try and nucleate research collaborations, but it seems like there's a lot of expertise here, and hopefully that can be a byproduct of that. And then, not to talk about National Jewish Health where I work, we have a gigantic number of pulmonary patients there as well. So there's really potential, I think, for a lot of exciting research to come out of these sorts of events as well. And I, again, wanted to thank John for his support, and I think he may have some concluding remarks as well. So,
once you're dean, you always have to make remarks. So just a few quick comments, and really to the commission and the commissioners. I hope that this showed you probably something you already know, this incredible wealth of expertise here in Colorado. Just sort of looking at the universities, the federal agencies. I think there's a depth of expertise here that should be very helpful for you as you grapple with these really very challenging questions. And, you think you've solved one and then another one comes along. So they are always going to be here. And I have to say, since coming here a year and a half ago when we've talked about climate or air pollution, the strength of the individuals, the research, their expertise, and their willingness to engage in helping translate it is really outstanding. So thanks to all the speakers, and thanks to the commissioners and everyone else who was here today. And then just really the last thing I wanted to say is that in planning this, we've had a really great partnership with CDPHE and working together, and I want to say that we're always eager to collaborate in holding this kind of forum to discuss critical issues. And then last, just thanks to the people who got the work done, the core support teams at CDPHE and here at the School of Public Health. It's been a lot of work done, and actually everything worked today. Isn't that amazing? And it sounds like you even found lunch in sort of our quasi-food desert here. So with that, thanks. And I think, Tricia, you're going to make... No, we're done. So, okay, all right, good. Then we're done. Let's go home. Thanks.